I want to nail down a couple more details that we didn't get to really address or reveal in our class today. So, kind of wanted to start from this question: why does potential energy equal zero at infinity? Well, if we think about a planet and something that is really, really far away, if you go far enough away, then the force, which is proportional to 1 over r squared, as the distance increases, that force is going to decrease. And it's going to decrease eventually. You get far enough away, effectively, the force is going to be zero. So if you stick an object way out here at such a large distance, then the force pulling it towards the planet is zero. Well, if there's no force pulling it towards the planet, then it's not going to have any potential energy because it doesn't have the potential to fall towards the planet. So effectively, at way out here at infinite r, at a very, very huge r, potential energy is going to equal zero. And if you let it go, then it also won't be moving. So the kinetic energy is also going to be zero. If you give it just a tap, just a little nudge, push it in the right direction, kind of like somebody sitting at the top of a slide, as soon as they start to get moving, they are going to accelerate toward the planet, and they're going to, as they do so, they're going to continue to speed up. So they are going to gradually have more and more kinetic energy. Now let's pause for a second and recognize, all right, well, at this really far distance away, we've got zero kinetic and zero potential energy. The grand total energy out at infinity is zero joules. So if energy is to be conserved, then as you approach the planet and gain kinetic energy, well, as we usually expect, you lose potential energy. But since potential energy started at zero, as far as record keeping goes, it makes the most sense for potential energy to be negative. So you're going to have a large amount of positive kinetic energy and an equally large amount of negative potential energy. So the math works out. Partly it's so the math works out. So essentially that's where we find ourselves. That is the approach that we're taking with the math in these gravitational situations. So where does that lead us? That leads us to a couple things. One, if you begin at a planet and launch, a ball, fire a cannonball out of a cannon, so fast that your goal is for it to leave the Earth's atmosphere, keep going, and eventually leave the Earth's gravitational influence, what you're saying then is that you're going to give it so much kinetic energy at launch so that at this very distant radius, effectively infinity, it will then have zero energy. So basically we're going to take this graph and work it from this point forward. So what we can say then is that at launch, you are going to have a kinetic energy and gravitational energy combined equal to zero. Well, whatever the energy is here, total energy is zero way out yonder. And so if the conservation of energy holds, then you must have had zero total energy initially. So happens that kinetic energy still conveniently is 1/2 mv squared. But as we've been saying, our potential energy is negative g m1 m2 over r. And those combined equal zero. So let's see if there's any sense we can make of this. Well, m1 is usually the bigger mass, the mass of the planet, for example, and m2 is, let's say, the mass of the ball, the thing that we're launching. And so that would also be the mass of the ball in our kinetic energy. So we could factor out that m, the mass of the ball times 1/2 v squared minus g times the mass of the planet over r equals zero. So picked up, we can cancel out the mass of the ball. So what we're left with is 1/2 v squared equals g times the mass of the planet over r. And if we, I guess we should be specific since we're talking about the r that we're starting at. So that is the r radius of the planet. And so rearrange things and solve for v. So v equals 2g mass of the planet over radius of the planet square root. That is the escape velocity. That's the amount of velocity that we need to give an object so that it starts at a certain distance r away from the center mass of the planet and continues out to distance infinity. That's the escape velocity. And when they say what goes up must come down, this is the exception to that. Literally, if you fire something off the surface of the Earth, ignoring air resistance, or if you could somehow clear the air out of the way, launch it, you would give it enough kinetic energy to effectively reach infinite distance, or reach a distance where the force would no longer pull it back to the Earth. So an object that goes up doesn't actually ever come back down. So let's keep this thought going. Now, that's a situation where we're going to send the two objects out to a position where the energy is equal to 0, which the only location for that to sort of be true would be at an infinite distance. Energy is 0 only at an infinite distance, where it has no kinetic energy and no potential energy. It doesn't have any potential to fall back to the planet. So you have to be absurdly far away for that to be true. But most cases, that's not true. In a lot of cases, we're talking about satellites, things that orbit the Earth or orbit the sun, or Halley's Comet, a 76-year comet, has this very eccentric orbit where something's going around the sun in a very, that's not a bad ellipse, I gotta say, a very eccentric orbit. And so what we're going to talk about now, conservation of energy as it applies to orbits. So at one point in the orbit, you're going to have a certain amount of kinetic energy and a certain amount of potential energy. And as you travel to other parts in your orbit, you're going to have, different amounts of kinetic and potential energy. But the grand total of those two is going to be the same. So I actually want to show a little image of what it looks like, so you get an idea of the speed of things. Full screen. All right, great. So looking at this green dot, slow, fast, slow. So as it goes further away from the thing that it's orbiting, it slows down and approaches, it speeds up, as you might kind of think. I wish I could pause it, but I can't, so I'm just gonna jump back out from that, maybe. And so we think about what's going on here when, I don't know, let's say it's orbiting in this direction. So when it's here, it's moving in this direction and it's being pulled toward the sun, toward the thing that it's orbiting. And so it's moving in the direction that it's being pulled. As you might expect, it's going to speed up. Its kinetic energy is increasing while its potential energy is decreasing. It's getting closer. Right? I was about to say it's not rocket science, but it literally is rocket science. On the other hand, on the way out in its very long orbital path, as it moves in this direction with some velocity, it is experiencing a force pulling it back in the opposite direction. And so as you might expect, it's going to slow down. So it's going to be losing kinetic energy while it's getting further away, and so it's going to be gaining potential energy. So all this goes to say energy is conserved no matter how you consider it. And the way we can represent that is with our usual energy conservation. Kinetic plus potential at one point equals kinetic plus potential at another point. Kinetic, conveniently, 1/2 mv squared. Potential energy is, again, negative g, let's see, the mass of the sun. Let's call this a comet, times the mass of the comet divided by the current radius, wherever it is, radius. That's effectively like where it's starting. At this point right here, we'll be curious to know how its energy changes once it gets to this point way over here. And so on the right-hand side, we've got kinetic energy again, 1/2 the mass of the comet times v, call it 2 squared at its further location, minus g times the mass of the sun times the mass of the comet over R2. So essentially we've got an overall expression that we're very familiar with and a trade-off between kinetic and potential. Our kinetic energy expression is the same as it was. The only thing that's different in this case is our potential energy expression. But once we know that expression, we can just go ahead and use that expression. The overall concept is still the same. So if you know a bunch of things, solve for the thing you don't know. Strong suggestion that this applies to one of the problems that you're being asked to solve. I think it's the Pluto problem. Now, the last thing to mention draws from this conservation of energy, but wants to take a look at one thing in particular, and that is the example where some orbits are perfectly circular. Imagine, let's pretend that that's a perfect circle, where the radius never changes. Well, if the radius never changes, then it's not going to get closer or further. That means it's not going to speed up or slow down. That means the velocity is not going to change either. So we can actually basically make a special case of this energy conservation formula. And that comes if and only if. I don't know if you've seen I with 2 F's, if and only if the orbit is circular, then we can revert back to circular motion stuff. And earlier on, or in another example, we derived that for a circular orbit, v squared is equal to g times m2 over r. M2. No, the mass of the sun, the thing you're orbiting. Mass, let's call this the sun. Sure, mass of the sun. So if we take our energy conservation formula, 1/2 m mass of the comet times its velocity squared minus g mass of the sun times the mass of the comet over r. Oh shoot, that should be mass. That should be r1 earlier. At its current location, but then remember that its current location is never going to change. So basically that's saying that this is going to be, we could just refer to that as the total energy. That's a constant. So there won't be a trade-off between one or the other. So if we plug that into there, we get 1/2 times the mass of the comet times g, mass of the sun, over r, minus g, mass of the sun, mass of the comet, over r. That's our total energy. Well, if we look at this carefully, we've got 1/2 g, mass of sun, mass of comet, over r, minus g, mass of sun, mass of comet, over r. These are exactly the same terms. So basically we've got 1/2 minus 1 of g, mass of sun, mass of comet, over r. So what that gets us is the total energy for a circular orbit is equal to negative 1/2 g m sun m comet over r. Since the radius is fixed, we don't have to worry about what the velocity is because it's not changing. And so that is an expression for the total energy exclusively for circular orbits, because the reason we got there was from our earlier derivation of centripetal force being applied to orbits. So that formula comes with a caveat. Probably went on a little bit longer than I expected it to, but I think I filled in all the gaps I wanted to. All right, good luck to you.